All right, so this is not meant to be read, but just to impress you. Just a few examples of recent applications of deep learning. I'm not going to go through all of them. There's been a lot of noise. And actually, I will come back to many of the applications in NLP at the end of the week, so you'll get a chance to see more of that. But so there's some pretty interesting things going on with speech recognition. Maybe Jeff Hinton did talk about that. Work going on at Google. I'm sure that Andrew talked about in vision and also in speech recognition, and I think they're also working in computational advertisement using deep learning. There was a nice article on the same day that I gave my tutorial at ICML in the New York Times about deep learning, talking about applications in speech, for example. So this is the speech stuff, language modeling. I'll come to that later. This is language modeling. This is some of the stuff we did. Also, sentiment analysis is kind of language modeling. MNIST is our old nemesis, on which we got a recent interesting breakthrough I'll mention later. And I'm sure Jan told you about the things he did. Let me come back to this notion of depth. You can represent most functions rather than any functions using a circuit where each node computes something and the output of the node depends on the result of other computations, which are the output of other nodes, and that forms a graph. So a neural network is a traditional neural network is a graph like this. So these are all directed acyclic graphs corresponding to actual computation you can do in the machine. And as I mentioned, most of the machine learning tools we use can be related to function approximation in the sense that you can represent a very large class of functions, like continuous functions, using like neural nets or formal neurons, RBF units, so that the things you find in Gaussian kernel SVMs, for example, or logic gates. And basically, in all of these cases, it's enough to have two levels. Like here, you can have ands, and here you have ors, in order to represent or approximate any function. So usually when it's continuous, it's approximate, and when it's discrete, it's represent. So as I said, this is nice. You can represent any function, but maybe you need a lot of these guys. In fact, maybe you need an exponential number of these guys. And so there are a few theorems, a few mathematical results that tell you that, in fact, sometimes, even though this can represent anything, it can be very inefficient, and you could represent it more efficiently if you had more than two layers. And maybe you need k layers, and k is something you don't know ahead of time. Depends on the data, the problem, the function you want to learn. So just some intuitive explanations. When you write a program, I'm sure you don't have something like this with a main program where everything is happening in one sort of sequence of instructions. Instead, you organize your programs as functions calling functions that are reused. And in a sense, we use depth all the time when we do things as engineers, for example. Same thing when we build circuits. The only kind of circuit that is flat, that has two layers, is a memory circuit. A memory circuit is basically, you put in the address, you look up in the memory cell, and you output the result. That's a memory circuit. But apart from the memory circuit, all of the other computational circuits have depth because that's much more powerful. I'm not going to go into this. So we have results on specific families of polynomials, as I mentioned earlier, but just want to mention we get these exponential gains for some families of polynomials and families of circuits for them. You can look up our paper from last year if you're interested. And there are some interesting, if you're mathematically inclined, there are also some interesting connections with what people do in complexity theory and circuits theory in theoretical computer science. For example, this paper from Braverman from University of Toronto shows that if you're modeling, if you're trying to represent a distribution, a joint distribution across n variables, and it's such that when you look at the marginals over k variables, in other words, you only look at subsets of k variables at a time, these k variables look independent or uniform. These kinds of distributions are hard, right? I mean, it looks like the variables are independent from each other. If you only look at k of them at a time, they look independent. But if you look at more of them, you can discover some structure. And then for these kinds of distributions, having more depth can give you exponential gain, basically, to represent the distribution. Okay, so basically this closed the motivations part. And you see here this complicated circuit, then a miracle occurs. Okay, so we need to look at more detail under the hood. I don't want to give you just nice words, but a bit of meat. So let's plunge. And I'm in the slides that are in my presentation, I'm guessing there's a lot of stuff that has been already covered last week, so some things I'll go quickly. But if you want me to spend more time, just raise your hand, say, can you explain a bit more? Please don't be shy. So I'm not going to tell you about basic neural nets, except one way to think about neural nets is you can think of the hidden units as doing a logistic regression, but where you don't need to specify the target for these logistic regressions should be. And it's just the learning, it's just a gradient on the final logistic regression that is going to guide the definition of what these guys should be doing. And you can stack them to have deeper nets. Then I have a bit about the chain rule. So I'm guessing that Jan covered the chain rule, but let me show you a little cute thing. So let's say I have a variable x that predicts y that predicts z. And so this is the basic setting where we're going to use the chain rule. We know dz, dy, and dy, dx. So what do these things mean? Dz, dy means if I make a small change delta y, I get a change delta z, which is delta y times dz, dy. So these are all scalars. And so dz, dy is sort of the constant of proportionality that tells me how a change in y translates into a change in z. And same thing for dy, dx. And now the cute thing is, if you plug this thing here, you get this equation. And now you recognize a chain rule. It says if I make a change here, delta x, the change delta z here is dz, dy times dy, dx times delta x. And that's the chain rule. It says basically how a change in x converts into a change in z is the product of the derivatives along the way. And you can generalize that using a Taylor expansion to say, well, if there are two paths by which x can influence z, then I just add up the products of the derivatives across each path, and you get the chain rule for more than one intermediate variable. Here you have two intermediate variables, and then you can have n intermediate variables. And then you can have a general graph where if I consider an arbitrary node x, the way this node is influencing z can be summarized by this equation where I'm looking at the successors of the node x, which I call y1 to yn, and saying, well, one way I can get the derivative of z, the final scalar output node with respect to x, is by summing the derivatives of z with respect to each of the successors, y1 to yn, these things, times the derivatives on the arcs corresponding to the connection between x and each of those successors. So that's sort of the generic rule. Once you understand this, you can apply backprop to any kind of situation, so long as you can compute these derivatives. And people have done that in many papers and many complicated settings. So backprop doesn't apply just on feed-forward neural net. It can be applied to any computation, so long as you can compute derivatives. And even if the derivatives don't exist everywhere, so long as they exist almost everywhere, you're okay, typically. So let's skip these sort of standard backprop and neural net things. Forward propagation, backward propagation, blah, blah, blah. You can do the same thing for recurrent and recursive networks. You think of, what happens as you unfold the computation into one big graph, as similar to what I was talking about, and then you apply the same rules. Same thing if your graph is a tree, that still works. And the tree could be something fixed ahead of time, or like in this example, could be something that depends on the data itself. So one of the nice things is that you can backpropagate through sort of switching. What it means is that if you have some variable, some decision, like taking the max, for example, that switches between different options. Like here, the juice flows either from A or from B into the output of the max. And that's a kind of switch, which depends on which one is larger. And for these kinds of functions, because it's continuous, you can not only compute gradients, but you can apply stochastic gradient descent, which is sort of the basic recipe that you can use once you have gradient to train models. One thing I'm not sure if you heard about, but maybe James Bergstra explained automatic differentiation, did he? Okay, so good. I'm not going to spend time on that. But I just want to mention, it's way more convenient to apply these gradient-based techniques when the gradients are computed automatically. You don't make as many mistakes when it's done by a machine, and it allows you to quickly prototype new ideas, new architectures. It's very convenient. Okay. So let's get more towards the things that interest us. In the old days of neural nets, it was all supervised learning. And so one question is, how do we do supervised learning in neural nets? So here's a very basic answer, starting with principal components analysis, which of course is even older. And what do we do in principal components analysis? We're trying to take a cloud of points and find a representation for those points in lower dimensional space. It turns out that it's enough to take the points and multiply them by a matrix that has less outputs than inputs, less rows and columns. And turns out that the right choice of matrix here are the principal eigenvectors of the covariance of the inputs in the case of principal components analysis. And then once you have that representation, which I called h of x, here h, you have input, you apply a matrix, you get latent features h, which you can think of as a coordinate on the manifold. Okay, so there's a connection between PCA and manifold learning. Once you have that, you can apply another linear transformation, which happens to be, the optimal one happens to be W transpose in PCA. And you can recover a reconstruction of x in the same space as x. So let's say x is here. When I do Wx, what I get here is a coordinate, like here, this is a two-dimensional input, and maybe h of x is one-dimensional, and it tells me where I lie on this line. So maybe here is 0, and here it's h of x. Now, that's a one-dimensional quantity, coordinate on this manifold. Then, if I remultiply by W transposed, I get reconstruction, which is again a two-dimensional point, but it lies on this line. Okay, so what we're doing here is projecting on this lower dimensional manifold, And when we reconstruct, we've lost something because we've reduced the dimensionality. And there's a reconstruction error, which is the difference between this and this, maybe squared. It turns out that this computation that we do with PCA is the same as what you would get essentially with a linear autoencoder. So a linear autoencoder is just a neural net that takes your vector and input, has a linear transformation and then another linear transformation, and then reconstructs and is trained to minimize squared error. So it's the same thing as PCA, except these guys are not necessarily orthogonal, and what you end up getting is a basis for the leading eigenvectors of the covariance matrix. There's also a probabilistic interpretation to PCA that is interesting and also connected to many of the models we do. And the probabilistic interpretation is that PCA is just modeling the input distribution as a multivariate Gaussian with a full covariance matrix that has this form. So it's lambda times the identity, so it's some constant in the diagonal, positive constant in the diagonal, plus W transpose W. So it's a low rank, this is a low rank matrix of rank equal to the number of singular vector eigenvectors we're keeping. So that's one interpretation. There's another interpretation which is kind of nice, which connects to things like RBMs and sparse coding, which is that we have these latent variables H, which actually correspond to putting values here, and then we apply a decoder W transpose, so we go from here to here, and we add noise, and this is how we think of the data being generated. So it turns out that if you marginalize H, in other words, you sum over all the distribution of H here, sum over all of the values of H under some prior P of H, which is marginal and which is factorized, then this becomes this, and you can also see that this W happens to be the same W here, and all of these things are nicely connected. Okay, so PC is a very simple model, but it has many of the ingredients we'll find in other models. It has this idea of mapping to a intermediate representation. It has an encoder and then a decoder back to the input space, and it has also these probabilistic interpretation both in the input space and introducing another way to think about it is introducing these latent variables which try to explain what you're seeing here. So PCA is part of the family of directed factor models, and what these factor models do is they have the structure I was talking about, but where the hidden variables H, which include H1, H2, and so on, are such that their marginal distribution factorizes. In other words, it's the product P of H is P of H1 times P of H2, and so on. In the case of PCA, each of the factors is Gaussian, and ICA, it's non-parametric, but you're assuming that they're independent, well, which is what this means. And in sparse coding, you're assuming that there is some concentration mass near zero. Although this is not completely true in regular sparse coding, but something similar to that. And then once you have generated these latent variables, you can generate X usually by just a linear transformation and possibly adding noise. And depending on your specific model, what you want to do is inference, so recovering H given X. And I'm sure at least Jan showed you plenty of stuff about sparse coding, so I'm not going to go into that. But the idea is your input is explained by a few of the factors being active at the same time. And then you can get nice pictures like this showing how one example could be obtained by combining different filters, and just a few of them being enough to explain your input. Now, PCA is very nice. I think it's very important to understand it well, and it actually is useful in practice. It's possibly one of the layers you can use. In fact, in our winning of the competition, the transfer competition, the first one last year that was had the results at ICML, we used PCA a lot as sort of the first layer and the last layer of all of our models. It turned out to be really useful. And in between we had like autoencoders and RBMs and stuff like that. Okay, but the game is we want nonlinear representations, and so we want to do something like stacking them, like you've seen for RBMs and autoencoders. And so PCA is not appropriate by itself, because if you compose two linear transformations, you only get a linear transformation, so that's probably not powerful enough. The nice thing about stacking nonlinear representations is that you are suddenly able to learn things that you weren't able to do. This picture shows what happens with a purely supervised net and some unsupervised pre-training on MNIST. So this is like old work from 2007, 2008, where we vary the number of layers and we look at test error on the y-axis. And you can see that like regular supervised nets tended to get worse as you after 2 layers as you add more layers, whereas these ones which use unsupervised pre-training were doing better, but still after 4 layers it got worse, so we still have some work to do. Or maybe that data needs 4. That's quite possible as well. Now there is a question, more research question, I think, which I want to raise here. Why was it that before 2006 it didn't work so well? And I think there's a lot we need to understand why training deep supervised nets is difficult. So I'll come back to this question of 2 of the explanations we've studied about unsupervised pre-training. Is it a regularization effect or is it an optimization effect? And we found that the 2 are present. And I think and the 2 are interesting, but the optimization difficulty is really troubling to me, because if we want to learn a machine that solves AI, if we want to solve the vision problem or natural language, all of these involve large quantities of knowledge that we want to embed into the machine. And if the machine is going to have all of that knowledge, it's going to have a lot of parameters, it's going to be big, it's going to have millions of parameters, maybe hundreds of millions of parameters. And we need to optimize all of these parameters. And if we have trouble training the networks I was talking about, we really need to understand what is going on. And when I talk to the Google people that are training these huge nets and looking at huge quantities of data, what they tell me is one of the main limitations they see currently with deep learning is underfitting. In other words, they don't even manage to get the training error down enough that they can do a good job. And I've been sort of facing and thinking about that issue for the last 20 years or so. And it remains a very understudied issue. For example, we don't really know if the optimization difficulties we're seeing are due to purely ill conditioning. So ill conditioning means that your second derivatives are very small in some direction and very large in some direction. And that makes optimization techniques like gradient descent not work well. Or is it purely a problem of local minima? Well, we know there are local minima, but we need to understand that better, and I'll show some results that help us understand that to some extent better, but still is mysterious a lot, or both. And there are some more complicated things going on. For example, let me show you some examples where we wanted to study the effect of examples early on during training versus examples later or at the end of training. So what this graph shows here, it's you can think of a number of examples, like fraction of the examples. So this was trained on 10 million examples, online learning. So in other words, each example is seen only once. It's coming from a distribution of deformed, randomly transformed images. And what we're plotting here as the y-axis is the effect of the examples at different points during training on the final function. So how do we measure that? What we do is, so here it says mean of the variance and of the standard deviation of to the mean of the variance of the output. So what I mean by this is, like, this is the first million examples. What we can do, because we have a whole distribution that generates these examples, we can repeat the same experiment, but using different examples for the first million. So we just, instead of getting the 1 million samples we had initially, we sample another million, but we keep the rest the same. Okay, so we repeat the same training, but changing some of the examples at different points in time. So here we change, for this data point, we change the first million examples. For this data point, we change the second million examples, and so on. So at this data point, we just change the last million example that has been seen. And then repeat that many times. And so now we can see how the function we get at the end changes depending on the changes we did depending on where we are in time. So for each of the neural nets we train, we get an output on the test set. We can measure the variance of that output across the different random changes of the first million, and the variance is plotted here. So in other words, depending on the examples I get at the beginning, the variance of the output function changes quite a lot compared to if I go in the middle of training and I change my examples to other examples, actually doesn't change a lot the output function. In other words, I could replace those examples by other examples from the same distribution, I get more or less the same output. Whereas the early examples seem to have a much stronger impact. So maybe this is connected to something people in biology and psychology called critical period, that the things that happen at the beginning of training that really matter, and after that it's hard to change. There is a little kink here which is easy to understand mathematically. It's just due to the gradient descent, which pays kind of exponentially more more attention to the recent examples. So that's a well understandable sort of recency effect. But the sort of these things are like the first few things you see in your life determine who you'll be later. That's what it says. And there are other experiments that suggest something similar. So in this experiment, we look at the filters. So that's the first layer weights, and we can do the same thing. Maybe these are first layer weights. You can do the same thing for second layer weights or third layer weights, but it's more pronounced for the first layer. You can look at them after unsupervised pre-training, and then you continue training the model, and it really works much better in terms of classification performance. But you look at the filters at the end of the second phase of training, which is supervised, and visually they haven't changed much. I mean, it's almost the same. If you look at the actual numbers, they're different. But the reason our brain looks at these two pictures and says, well, this is the same, is because the sign of the weights didn't change mostly. And our eyes really care about contrast. So what does it say? So the sign of the parameters haven't changed during training means that we started with the parameters near the origin, and then early on they chose to be in some quadrant, which means picking the signs. And then once you're in that quadrant, that's it. You stay in that quadrant. So, and the signs, if you think about the logic of what is being computed, it's mostly determined by the signs. So it's not surprising that the early part of training has such an influence. Yes?
Are those first layer weights actually important to performance? After training the entire deep network, you replace just the first layer with the weights that have the correct sign but not the correct value. Would there be a substantial change in performance? Or?
So I think we did that experiment, and we tried, like supervised fine-tuning only the last K layers and something like that. And that's in like a GMLR paper, 2010 or 2009. And the answer is yes. The fine-tuning makes a difference. Now, Specifically, maybe the first layer, there isn't so much of a difference, I'm not sure. And the higher you go, obviously, the more impact it has. And also that effect here is, that effect is more pronounced for the first layer than the second layer than the third layer. So yeah, the answer is that indeed, in terms of effect on classification error, the first few layers have less, and you could replace them by the initial ones. Well, you could force them to be fixed during fine-tuning, and you wouldn't lose as much. But still, there is an impact. There's another experiment which goes in similar direction. It's connected to a paper I wrote for ICML 2009 called Curriculum Learning. And that's also kind of inspired from knowledge of how humans learn. So we learn by taking advantage of the concepts that we already know, and our teachers use that. So they introduce the concepts as soon as we're ready, hopefully. And I hope you're not completely lost by what I'm talking about. Otherwise, there would be no point in listening to me. So that happens to me when I go to a conference and I don't understand what, the jargon, because we're much more efficient at learning if we see things that, for which we understand the basics and the concepts, and then we just can compose new concepts on top of the things we know. So in this paper, what we explored specifically are two things. So one is an idea from a computational or optimization perspective, why ordering examples in a smart way could make the optimization problem much easier. And we talk about the notion of continuation methods, where you instead of optimizing directly something difficult that has many local minima, if you start by optimizing something simpler, maybe you only show the student simple prototypes and simple concepts, examples of simple concepts. And then the student can learn that easily, and the problem doesn't have as many local minima. And once it's mastered, you kind of introduce slightly more complex elements in your examples, which correspond to changing the cost function to something that has more local minima, but now you're already in a better region in the space of parameters from which you can move towards better solutions. Anyway, I won't go too much into that, but we also did experiments where we consider, for example, in language modeling, two situations. One where a learner sees random text from Wikipedia, randomly selected sentences, and another where initially the learner only sees sentences that are easy because they come from words that are very frequent, like baby talk. You take the 2,000 or 5,000 most frequent words. They are the words that are sort of more common in language. They are easier to understand, probably. And if you just train with sentences containing only those words, and then you gradually introduce more vocabulary, then it turns out you get much better results. Yeah.
In other contexts, could that work with something like training it on the first few principal components of your output vector, or would that be a bad idea?
Maybe I don't really understand your idea.
Well, so in other contexts, you might not have something like, the most common word.
But this is about selecting the examples or sort of organizing your examples in a particular way. It's not about the architecture.
So some examples from opposite ends of the first few principal components.
Oh, I see what you mean.
Or would that lead it to learn some spurious way of separating?
Right. So some of the experiments we did and others later, I guess I'm not setting them here, but somewhere else maybe. At the last NIPS, people actually did experiments with humans, and they found that, so this is a group by Zhu and collaborators, they found that humans like to teach by showing prototypical examples, and not like in active learning where you try to go to the examples on the decision surface like that are really ambiguous. In fact, humans don't like ambiguous examples. They like to start by really easy prototypical examples and then gradually move towards the more ambiguous cases. So that seems to be how humans teach, and humans don't like to be taught the other way. I don't know, maybe that helps answer your question, but we can talk about it later. So there's one of the things we did to try to understand why training deep nets is difficult is in this AI Stats 2010 paper, where it's a lot of sort of empirical observation, just study what's going on in the networks while you train. At the end of training, look at the distribution of activation, so the outputs of the units, the distribution of gradients, both the gradients on the units that you get from backprop and the gradients on the parameters, considering what happens at different layers, what happens as training progresses, what's the effect of different initialization, and we found a big difference, and we proposed in this paper a particular initialization technique based on our understanding of what was going on, and for different nonlinearities. So I think that helped my understanding a lot, and encourage you to look at that. Okay, so I'm assuming that you've been explained the basic recipe for unsupervised pre-training. This is sort of the autoencoder version. You train a layer of features that are good at reconstructing your input. Once you've done that, you can throw away the decoder, and you use that as input for training a second autoencoder in the same way, and so on, and you learn more abstract features, and then you can initialize maybe a deep supervised net. So that's sort of one of the basic recipes we've been using, and you can do that with RBMs. So I'm gonna skip the part on RBMs, assuming that you have covered that material, but if you feel that you want me to come back to some of the things, just let me know, and I'll do that at some other time. So a bunch of slides on RBMs. There'll be some things I want to mention. Free energy, gradients, positive and negative examples. So I assume you've understood that picture. I want to put it back again. I guess Jan and Andrew and Jeff probably explained these things. Yeah?
This question mentioned when you have different initializations, you have
Yes.
different results, right? Have you tried combining the results and see if you get like a much better combined result?
What do you mean combining the results? I mean, initialization is a recipe to start
Or like pooling the networks that are trained
with different initializations.
Exactly.
No, we haven't tried that. I guess it might be a good idea to have some units that are more saturated, have larger weights, and some that don't, but haven't really done that. Different training procedures. So I imagine you've heard about contrastive divergence and PCD, right? Did you? And fast PCD as a kind of heuristic variant of PCD, which is very interesting. Herding, it's okay, we don't need to go through it today, you don't need it later, but it's an interesting variant that's related to fast PCD. Tempered MCMC is an interesting idea. You probably didn't hear about it, but you might hear it from other speakers next week. And then, the idea is to introduce more noise in the stochastic model, more noise in the Markov chain that helps you to escape modes, to move from a region of high density to another region of high density, which would otherwise be difficult. This idea of making chains that can move from mode to mode, I'll come back to, and I think it's a pretty interesting and important one. So CD, so these are the more details on these things. I want to show you some pictures just for the fun of it. So we came up with this RBM variant, which works quite well for modeling the statistics of images, at least on a small scale. So these are 32 by 32 CFAR 10 or CFAR 100, I'm not sure, images of objects. And what you're seeing here are not the images in the training set, but these are the images generated by the model using a Gibbs sampling. Now, maybe you're not impressed, but when I saw this, I was impressed, because if you've ever tried to generate samples from a model of images, it's very hard to get anything but blurry, meaningless stuff. And here we see objects, and we see, you know, background, and just see a comparison. These are the training examples, and these are the same generated examples I showed you. And what we've done is we've looked for each training example, for each generated sample, what was the closest training example in terms of the input image. So like this is a close-up here. So like this generated sample, the closest in the data set is this, which happens to be another, well, a boat. I don't know if that's a boat, but it could be a boat. And this is amazing. I mean, this generated this thing. I see an airplane. I mean, it's not the same as a training example, but so it's not cheating. When you generate from a probabilistic model, you have to be careful that it's not just copying your training examples. Right? You could easily train a generative model that just learns by heart your training example, and when you sample from the model, you get your training samples, maybe plus a little bit of noise. And that would look nice, but it wouldn't be nice, and wouldn't be interesting anyways. So here, this model actually generates things that are not near copies of training examples, but do look like the same kinds of images. So there's been a lot of progress, I would say, in modeling image texture and structure in the last few years, in part thanks to things like these variants of RBMs. Now, the main sort of thing I want to talk about, yes?
Is that because the model was convolutional, or is that because the spike and slab RBM is great?
All of the above. So if it was not convolutional, well, I guess having local receptive fields is important. As we've seen, you can get away with a thing called tiling, where you don't actually share weights across different positions, but then you need more examples. There's one trick here, which I didn't mention. Well, a trick. I mean, it's an architecture choice, which is that we have hidden units that look at little patches, I think maybe 9 by 9, and we have some hidden units that look at the whole 32 by 32. So why this is important? Because in these images, you have both sort of texture that could be anywhere in the image, and you have this general idea that because of the way these are all pictures of objects, you see, and the object is always kind of in the middle. So this is not at all translation invariant. You have like a central thing in the middle. So you need some units that look at the big picture of the whole image and not just at one little patch at a time. So that's one of the tricks we used. Yeah.
So this was done with just one hidden layer?
This was done with just one hidden layer, yes. But the hidden layer was quite complicated. So we not only had this convolutional structure, but the spike and slab RBM has these two kinds of hidden units, the spike and the slab. And we had multiple slab per spike units. So these spike units are binary units, and the slab units are real value units. So there was quite a lot in the design of this one hidden layer in terms of the structure of the model, the energy function. And like we did a lot of exploration of the structure and the hyperparameters before we ended up on this. All right, so autoencoders. So I already tried to explain the basic idea of inputs being transformed by some nonlinear function or linear function, but that's boring, into some code space, and then decoded by another function, and then you get a reconstruction. Here I just write R of x. So here are some examples, just a one-layer encoder, a one-layer decoder, and then squared error reconstruction. The traditional things we've seen with PCA is where the encoder is outputting a vector that's of smaller dimension than the input. So it creates a kind of bottleneck. And you can think of the, like in PCA, for example, you can think of the representation as a new coordinate system, a lower dimensional coordinate system. But actually, one of the big lessons from the last few years is that we can sometimes, or most of the time, get better results by having the intermediate representation being bigger than the input. Now, if your input is huge dimensional, like a whole sentence, because each word is taken from like 100,000 choices, and you have 10 words, then usually it's not going to be bigger. But when the input has a reasonable size, like a 32 by 32 image is only times 3 RGB, so that's only like 3,000 numbers. Well, typically, more than several thousand here works best. So the SSRBM I was mentioning has quite a lot of features as well. Okay, so the encoder and decoder can have at least one, but could potentially have more layers. And there's this interesting thing that's well known for a while, which is if the encoder has many layers and the decoder has many layers, then actually training this from scratch is very difficult. But of course, one of the first things that have been discovered since 2006 is you can train very deep autoencoders if you pre-train them layer by layer. As we've seen, there are some connections between contrasted divergence training and reconstruction error. I'm not going to go into this, but just so that you know that there are some connections. Basically, it says that when you minimize reconstruction error, you actually do something that's not too far from what you do in contrastive divergence updates. Okay, so this is kind of more difficult to understand material, maybe different from what you're used to thinking. And it's motivated by my attempts over the last few years of trying to understand what autoencoders do, what Jan's, for example, predictive sparse decomposition is doing from a mathematical point of view. Because we have these training criteria and we optimize them, but what do they mean in terms of modeling the input distribution? So here's a first take on what they mean. Well, first of all, let's try to put down some notation here. The traditional way we do machine learning, and this is like 99.99% of what we do in machine learning, is like this. We imagine that the world comes about by having some parameters coming from some prior distribution. So that's like the Bayesian way of thinking, but you can, you could generalize that. And then, given the parameters, we have some likelihood function that tells us how the data is generated given the parameters. Okay, and one way, and then we can parameterize this and parameterize this separately. So we have a separate set of parameters for the prior and for the likelihood. And one way to generate the likelihood is, for example, to have an energy function. So you've seen this a lot last week, like the RBM energy function. And then to actually get a probability, you need a normalizing constant, which is called the partition function. But here I highlight the point that this partition function, this z, is a function of the parameters, because it's the integral of the numerator, which is e to the energy function, over x. So what remains, there are x and thetas in the story, so I integrate out the x, I get still some thetas. And then the bad news with all of the probabilistic models you've seen is, well, first of all, computing this Z is intractable because it requires summing over an intractable number of configurations of X. And computing the gradients is intractable for the same reason, because it involves this same sum. And we need that in many models to get a gradient on the parameters. So in the gradient, you have the gradient of the energy function weighted by the probability of that configuration of the inputs. Okay, so you've seen these things before. That's the usual way of thinking. Now let's consider, now that you've seen that notation, let's consider a different way of thinking. Let's parameterize our joint distribution between data and parameters like this. So now I have an energy function here, which is different from the one before because it depends both on x and theta, and in a sense it tells me about the joint of x and theta. It's not x given theta, and really what it means is the integral I'm going to put here, the partition function, is over both x and theta. So in the previous slide, here this was integrating only over x, and then the integration over theta is happening in the partition function, or the normalizing constant for the prior. All right? And here I'm saying, okay, let's put everything in one pot. I'm not going to make this decomposed into two parts, one for the likelihood, one for the prior. I'm just going to have one sort of big energy function, the joint energy in parameters and data for Geppara. And okay, so I can do that. I mean, it's a legal way of thinking. It's just a more general kind of model in the sense that we don't assume that the joint is obtained by separately parameterizing the conditional x given theta and theta on the side. And now the good news is the z here, because it integrates out both x and theta, I don't care about it. I mean, I can compute the derivative of this z with respect to theta, and it's 0 because there's no theta in it. So what's the magic here? The magic is if I compute the derivative of the log of that with respect to theta, I just get the derivative of the energy with respect to theta. There's no partition function. Now, of course, there's no real magic in the sense that this joint energy function, if I apply it to the model like we used to have, is going to have this is the usual energy function plus the log of the usual partition function minus the log of the prior. So it still has this thing, but that's if we stick to the old way of thinking. But we could write other energy functions, joint energy functions, that don't have this kind of structure and might still be interesting models of x and theta. And what I'm claiming is, as soon as we minimize some criterion, like reconstruction error with a regularizer, for example, we can interpret it as maximum likelihood jointly on x and theta. So I guess this is just food for thought for now. But more importantly, there is a lot of progress that I've made, at least in my mind, to understand what autoencoders do. So you could apply this thinking to autoencoders and then say, well, reconstruction error plus a regularization penalty is just this joint energy function. And it's nice, but I didn't know how to use that. Like, well, we actually tried sampling from the model. Once you have a probabilistic formulation, then you can say, well, okay, I stick my training criterion here, and I consider that's the probability, basically, with the exponentiation. Then once I have a probabilistic model, I can do things with it, like marginalize some variables or sample or things like that. But up to now, I haven't been able to make that work with samplers like hybrid Monte Carlo, which work for continuous variables. But I've gotten sampling to work for autoencoders using a different route, which is what I'm going to tell you soon. But first, let me tell you sort of in a summary what I've learned in the last few years, and especially this year, about what autoencoders do. So first of all, there's an easy picture, because we know we minimize some kind of reconstruction error. It doesn't have to be actually squared error. It could be, like we often use cross entropy and things like that for discrete data. But anyway, it's some kind of reconstruction error. So this is the input, this is the reconstruction of x, and this is a scalar function of x. So if you imagine x space, what we're doing is minimizing reconstruction error at the training examples. So the optimal sort of autoencoder, what does it do? Well, it puts a hole, it carves a hole of reconstruction error at the training examples. In other words, if I take a training example, I can reconstruct it. But if I take anything else, especially far from the training examples, it's hopefully going to have a large reconstruction error. What makes it large outside of the training examples is because I'm using some kind of regularization. So it's very important, I'll come back to that, that there are some constraints or some kind of regularization that forces the autoencoder to poorly reconstruct the input far from the training examples. So you're going to get these peaks, ideally. Okay, so now we understand a bit of the connection between autoencoders and probabilistic models, and in fact that's been the thinking for many years. That's what they do, and so sort of Jan's way of thinking about it is okay. So it's just we can take the reconstruction error and consider that to be an energy function, and you know if you take e to the minus this, you get like a density, and you know what I had here actually is going to give you something similar, because this energy function is going to be basically reconstruction error, maybe plus some regularization. So you're going to get these holes near the training examples. Fine. Okay, so that's kind of the obvious thing that's been known for a few years, but it's good to fix your mind on that. If you didn't know that, it's good to understand what we're trying to do. In what ways is this modeling the input distribution? Well, first of all, it's trying to make reconstruction errors small, where it thinks that there are highly probable configurations of the inputs. And how is this going to generalize? Well, in the same way that the probabilistic model is going to generalize by putting probability mass in new places. And here it's going to generalize by having small reconstruction error at other places than the training examples. For example, maybe there's actually a line in input space where these three training examples line up. And along that line, it's also going to have small reconstruction error. And in that case, it's going to learn a kind of manifold, and I'll come back to that later. But there's more to the understanding, and this is kind of a summary. I'll spend more time in the details. I guess it's going to be, am I almost done? Yeah, I guess so. It's going to be tomorrow. So this is like a advanced summary of what I'll do tomorrow. So here's some of the things we learned. One is that the vector difference between the reconstruction and the input points in the direction of increasing probability. In other words, this is a scalar, but if I just look at the vector difference itself, it's a vector that, if you think of it as starting at the point x, points towards r of x. And that happens to be the direction where the model thinks we should go if I want to move towards higher probability. And that happens to be something that has a mathematical sense called the score, which is the derivative of the log density with respect to the input. So this p here is the model that is the model. It's not the true generative density. It's what the model has estimated. So according to the model, the direction that one should go to increase density as much as possible is that direction. So we've learned that. And it's also connected to something called the local mean, which is if you're at some point x and you look in the neighborhood of x and you look at the mean of the density in that neighborhood, where is that going to be around x? And that happens to be the reconstruction as well. And then there is some really exciting thing about the local covariance. So local mean and the local covariance, you can think of allowing you to approximate a density locally by a Gaussian. So at every point in input space, you can imagine you approximate your density by a little Gaussian, and you can have many little Gaussians everywhere, at least in virtually speaking. And it turns out that the reconstruction and its first derivative, which is its Jacobian matrix, give you the local mean, respectively, and the local covariance. And that's also connected to the second derivative of the density. So in other words, what this stuff is saying is that autoencoders estimate some local property of the density, the first and second derivative, and the local mean and local covariance, which happen to be, closely linked to each other. And using this understanding, we've come up with sampling algorithms for autoencoders, which I'll talk about tomorrow. All right, I think I'm done for today. If you have more questions, I'll be happy to answer.